In this lecture, we are going to discuss the equivalence principle in its different formulations: weak, medium strong, and strong. But before we do that, it is convenient to start by explaining why we want to talk about the principle of equivalence. In the very first video in which we discussed the principle of special relativity, we concluded that it was necessary to reformulate all the laws of physics which were not in agreement with the principle of special relativity, which were not Poincare invariant. As I'm going to explain in just a little while, Newton's theory of gravity is not in agreement with that principle. It's not a special relativistic theory of gravity and needs to be reformulated. Well, reformulated or will replaced entirely by a new theory which for small speeds reproduces the Newtonian theory. So let me start by reminding you what Newton's theory of gravity is like. Oh, probably you know the law of the universal law of gravity, but we need a better formulation in terms of fields. And this formulation can be made in terms of the gravitational potential Vg and the density of matter rho. The law that tells you what is Vg if the source of the gravitational field is rho is that this Poisson law. So this would be Newton's constant and this would be rho, the matter density. In particular, this law, which is an expression a bit more general than the universal law of gravity, implies the universal law of gravity. If you have a particle, a point particle at the origin, and it has mass m, then the density is just this mass m multiplied by a Dirac delta function at x. Okay, then you know that the solution to this equation, Laplacian Vg equal to 4 pi Gn delta 3 of x is Vg equal to minus Gn m divided by the absolute value of x, or r if you want. Okay, this is the Newtonian potential for a point particle at of mass m placed at the origin. And okay, we can find the field gravitational, the intensity of the gravitational field, okay, that we can call Eg as minus the gradient of Vg, and this just gives you minus Gm divided by r squared and then r divided by r. The force that acts on a second particle, a small of mass small m, could be m times Eg, so it will be minus Gmm divided by r squared divided by r, and this is the universal law of gravitation. And then the motion of the particle could be dictated by the second law of dynamics. So this F is the mass of the particle times the acceleration, as you know. Okay, before I start explaining why this is not relativistic, although this is more or less obvious maybe, let me mention that this is very similar to electrostatics. Okay, the main difference with electrostatics is this sign here. Okay, and let me put it in red because really it is a very important difference. Okay, that causes is responsible for many of the things that are going to happen and of how electromagnetism differs from gravity. Okay, why doesn't this law satisfy the principle of special relativity? Okay, we can look at it from many points of view. First of all, instead of 4 4s, a full relativistic vector f mu, we only have f. Okay, a vector. One needs to add something else, but it's not clear how to do it. A deeper reason would be that this law does not describe what is the field of a moving particle. It is in principle designed to describe the field produced by a particle at rest, and then by lack of any other laws, as different from what happens in electrostatics. In electrostatics, there are additional laws. These additional laws tell you what happens when a charged particle moves. So from this motion, for instance, you deduce that electromagnetic waves are created, and that a charged particle which is at some distance will receive the signal that the other particle has moved, and the electromagnetic field is changing because the other particle moves at a time which is not instantaneous but related to the distance and the speed of light. Here there is nothing like that, so you are forced to assume, okay, by lack of any other information, that this law is valid even for particles that move. And the problem, if you want, is that for a long time, using just this law and with that assumption, one got very good results for the orbits of planets, for instance. There was no reason to believe that any more laws were necessary. The reason is the principle of special relativity. It tells you that even if the numbers could be that one gets are good, there is a matter of principle that the signal of that the mass has moved here. Okay, this one is moving, then the field that it creates at the position of the mass m, which is at a distance L, the signal that this has happened and the change in the field has to take a time larger than L divided by C. Okay, so this signal has to propagate at a speed smaller than the speed of light. For all the reasons that we explained, also this signal has to arrive as a wave, and there is no wave equation in this law. All this tells you that this has to be modified. Okay, so how do we modify this law of gravity? Okay, the simplest thing would be to replace the field V, this potential field, Vg, the gravitational potential, by some other field. The candidates would be a scalar field. It could be a component of a vector field. We know that one possibility for obtaining a potential in the action of a point particle, okay, in the non-relativistic limit, it would be to have A0 equal to Vg and the rest of the field. So one possibility is that the full gravitational field consists of more components, and that one of them corresponds to the gravitostatic potential, but there are more, and the laws are similar to those of electromagnetism, and they tell you that the signals of gravity propagate at a finite speed, probably c. There are other possibilities. The next possibility in complication would be to assume that it is a field of higher spin. So this is a field of spin 0, this is a field of spin 1, and a symmetric tensor would describe a field of spin 2. Okay, so this would be the first thing that one can think about. Another modification that needs to be done is the following. In the Newtonian theory, the source for the gravitational field is the mass, or the mass density. However, in special relativity, we know of the equivalence between mass and energy. So the source of the gravitational field has to be the total energy. Okay, whether it is in the form of mass or other kinds of energy should not matter. So it has to couple, the gravitational field has to couple to the total energy. Well, this is not so easy to do with spin zero field. But let's think a bit on what is the source of a field. In general will be some kind of current, that you can couple to this field. You can couple to phi a scalar current, and if the source of the gravitational field is the energy, and the energy we know that it is not a scalar, it is not a spin zero field itself, the density of total energy is part of a larger object, of a tensor, in fact a symmetric tensor we expect, which is the energy momentum tensor. So this tells you that this cannot be. And if you try to construct theories of special relativistic gravity with a scalar field, as people did in the past, these were some of the first trials by Nordstrom and others, you will fail, in the sense that what you get will not correspond to what you expect from a theory, a special relativistic theory of gravity. In particular, for instance, what you get from the deviation of light rays by a scalar field is wrong. Okay, so the next possibility would be A mu. A mu does not couple directly or easily to the energy momentum tensor, but okay, let's consider this for a moment, and you could think first of the free gravitational field, just as one can study the free electromagnetic field in absence of sources. Okay, there are other problems with the spin one field. One of them is that because of this sign that we remarked here in red, if you describe the gravitational field in terms of vector field, the spin one field, you will find that gravity waves would transport a negative energy, and you don't want this. There are other problems a priori with the spin one field, and those are that it gives an interaction which is repulsive between like charges of the same kind or sign. These problems alone tell you that the spin one field is really not a good candidate. So the next candidate could be the spin two field, the next simplest. And constructing a theory, a special relativistic theory, if spin 2 was only done by Firth and Pauli long after general relativity had been constructed. Why? Because, what I'm telling you is a logical story, but it's not what happened historically. Before people consider the construction of a theory of gravity in terms of a spin 2 field, special relativistic spin 2 field, the principle of equivalence was used as a guide to construct that theory. Okay, this in any case suggests that there is something special about this spin 2 field, and indeed it is related to the metric that we have advanced, that it is related to the gravitational field. That was one of the main ways of recovering in the non-relativistic limit potential, the gravitational potential in the action of a point particle, just to modify the metric, adding in one of the components something that it is just the gravitostatic potential, for instance. In more general cases, there will be more active terms in the metric. This has the ring of truth, and indeed, one could recover general relativity from this spin 2 field. But the path to do that is very long and very difficult. It is plagued with conceptual difficulties that one has to solve, and really it was only learned how to do this in the 60s or even later. So this is not easy, but of course you should know this formulation. As a matter of fact, one recovers this formulation in terms of a special relativistic spin 2 field in the weak field limit of general relativity. So, although logically one would arrive to this proposal of a spin 2 field soon. Okay, historically this is not how it happened, and also to arrive to this formulation is much better to start from general relativity and obtain it a weak field limit. Okay, in fact, we will in this weak field limit, this h mu nu will be the field that supports gravitational waves, just like a mu supports electromagnetic waves and phi scalar waves, if there is such a thing. Finally, observe that if really the source for the special relativistic gravitational field has to be the energy momentum tensor, because energy and matter are part of this larger object, so they are not part of just one index current or a scalar current, but really of two symmetric index current, then the thing that couples naturally to it is h mu nu. So it is an option which is quite natural from the special relativistic point of view. Okay, since the historically it was the equivalence principle that inspired the path to arrive to general relativity, this is what we will study next. But this is important for you to know.